My name is Nitin Pai, and today I'm going to teach you about the Gauss Law. The Gauss Law, as we can see, is the electric flux equals the charge inside the area divided by E naught, which is a constant. And this law is basically used to find the electric field along a closed surface. So before we delve into the depths and applications of Gauss's law, let's figure out what this means. So let's get rid of this. EDA, integral along a line. This means the electric flux. And to solve for the electric flux, you're taking the integral along the shape of the electric field at each of these little areas. So, for example, let's draw a sphere. So this is the y, x, and z planes. So what you're going to do is you're going to find the electric field at each point on the sphere and add them all up. And that's basically what the electric flux is. Let's now figure out how to use Gauss' law to do some physics. So, an easy example, a good first start, would be solving the electric field around a point charge at any point. So let's say this is positive Q, and the point we want to figure out is going to be right over here. So, to use Gauss' law, we must first pick a Gaussian surface, and a Gaussian surface can be any surface you want, except it must satisfy one condition. Any point on that surface should have the exact same electric field, because that will make solving the flux a lot easier for us. So, what I can do here is pick a sphere. Imagine that's 3D. So any point in that sphere, because it's equidistant from the point charge, it'll have the exact same electric field. So now let's use Gauss' law. Because it's going to be the exact same field at any point, the integral is just going to be the field times the area. Surface area. So I guess we can solve for the field. Now plugging in the formula for the area, you get the formula. So this would be the formula for the electric field around a point charge at any point around, at a point R, anywhere away from the point charge. And if you would remember, this is exactly the same formula as Coulomb's law, which we learned earlier. So I just proved Coulomb's law using Gauss' law. Alright, now we're going to use Gauss' law to figure out the electric field at a point near a line of infinite length of charge density lambda. That's what I've got drawn here. So, if you remember, the first step is always to pick a Gaussian surface. So, I'm going to pick a cylinder. Imagine that's the same length on each side. So now that we have our cylinder, the top and the bottom parts of it do not contribute to this because they are perpendicular to the line of charge. So, writing out our formula, again, the field is going to be the same at every point, so you can just multiply the field times the area. First, we gotta look at the Q enclosed, and the Q enclosed along this entire plane is going to be the charge density times the length. So let's call that lambda h. So now, E equals QA closed over E naught A. You can start plugging in numbers here. E equals lambda times height over E naught times 2 pi r times height, because that is the surface area along the body of the cylinder. So we can cancel out the h's and now get E equals lambda over 2 pi r times E naught, which is going to be the formula. Alright, now we're going to use Gauss's law to solve an example which is commonly used in physics classes. So here, this setup is going to be a non-conducting sphere on the inside with an even charge distribution of Q with a spherical shell around it. So now what we can do is use Gauss's law to solve the electric field at many different points in the setup. So first, let's look at inside the first non-conducting sphere. So let's say our point we're looking at is radius r away from the point, and it's less than r8, which is the radius of the sphere. So first, let's figure out how much charge is enclosed inside the surface. Sorry, the surface we're going to pick is again a sphere inside it. So the Q enclosed is going to be the ratio of the volumes of the two different spheres. Sorry, of the Gaussian sphere to the sphere for a spherical shell. Sorry, conducting sphere. So 4 by 3 pi little r cubed divided by 4 by 3 pi big R, RA cubed. So we can cancel out these two. So the Q enclosed is going to be R cubed over RA cubed. And now we can go back to the formula and plug this in. And again, since the field at any point in this sphere is going to be the same, it's going to, so we can again just multiply the field times the area. So field equals Q enclosed over E naught A. And now we can plug in variables to figure out and now we can simplify this a bit to get E equals Q times R over R cubed, big R cubed, not 4 pi. So this is going to be the formula for inside the first non-conducting sphere. Alright, so the next area we're going to look at is going to be between the non-conducting sphere and the spherical shell. So this area over here, let's say the point over here, which is, again, r away from the center. What we can note here is that the charge enclosed in this area is always going to be equal to the entire charge in here. So I guess that's simple. Q enclosed equals Q. So now we can solve for the field. And just simply say that it's going to be Q over 4 pi r squared E naught. Alright, so now we're going to look at the field inside the conducting shell. So let's take a point over here. First, before we do this, let's study the science of this conducting shell. So what happens is, since there's a positive charge inside here, it induces a negative charge along the inside of the shell. So all this area is going to be negative, and what that does is, again, induces a positive charge on the outside. So there's, again, no charge inside here. So let's say the charge inside, charge over here, no, it has to be this way, the charge inside here has to be equal to the charge over inside the sphere. So this is basically going to be equal to negative q. So let's look at any point inside here. The q enclosed is going to be equal to 0. Why? Because it's always going to be this minus this. Sorry, this plus this. And since this is negative and this is positive, and they're the same magnitude, it's going to be 0. So we can just simply say the field is going to be 0. So the last thing we're going to look at with this entire setup is going to be outside. So let's pick a point outside of this. That's r away again. So again, our sphere is going to be out here. And guess how much charge is enclosed? Everything. So q enclosed equals the q of the sphere plus the q of the shell. And q of the sphere, as you can guess, is q. Awesome. And looking at the shell, the net charge is going to be 0 because negative on the inside equal to this, and this positive on the outside equal to this, so plus 0. So going back to the Gauss's law, E equals Q enclosed over E naught times 4 pi r squared. I'm going to be lazy and just erase this and say this is your formula for outside.